we are continuing the proof of the existence of a Jordan decomposition. Okay, so let's recall where we were last time. Okay, so we have a linear operator T from V, linear operator. Okay, where V is a complex vector space. Okay, and we first reduced to the case that that 0 is an eigenvalue of T. Okay, then we defined the following, which is Ki is the kernel of the T composed with itself I times. Okay, and what's the notation? Ui is the image of T composed with I enough times for all one less than one for all I greater than or equal to 1. So we defined. Okay, so then the Ki is an increasing or weakly increasing family of subspaces of V, and the Uis are weakly decreasing subspaces of Vi of V. Okay, and then they must stabilize at some point. So we defined. So there exists M such that Ki is equal to Km for all I greater than or equal to M, and Ui equals Um for all I greater than or equal to M. Okay, so we define K to be Km and U to be Um. Okay, and we showed that V is K direct sum U. Okay, just a minute. Sorry, I just need to look at last time's file. Yeah, we also showed that they are T invariant subspaces. For a minute I forgot whether we showed it. Okay, and that U and K are T invariant subspaces. Okay, so this will help us. So if we find a basis for K and a basis for U, okay, and then use that as a basis for use their union as a basis for V, then the matrix of T will be block diagonal. Okay, so that's the reason why we want to decompose this into to direct sum of T invariant subspaces. Okay, so this is where we were. Okay, so now, okay, so continuation. So this is from last time. Okay, so now let us. Okay, so we would now like to do induction.
Hello, sir.
Yes.
Sir, could you briefly mention once the line of proof for U and K being proper subspaces?
No, I have not said that.
Oh, okay, sir.
I did not say that.
Oh, okay.
I just said they're T invariant subspaces.
Okay. Sir, in the previous class, once you mentioned that whether they will be 0 or V entirely or not.
Yeah. So
okay,
no, they need not be Okay, we will see that now. Just a minute. Okay. No, it is not that. I mean, it is not necessary that both of them are proper subspaces, and it is not necessary. That is not required for the proof either.
Okay, okay, sir.
Yeah, it could. I mean, okay. So things we know. K1, which is the kernel of T, okay, is not zero because T is uh, uh, because since zero is an eigenvalue of eigenvalue of T. Okay. Okay. So I mean, what we need about properness of which of the subspaces is here. Okay. So which means that U1 is not V, right? Because K1 directs, I mean, K1 directs and U1 is V. That is a rank nullity theorem. Okay. So K1 is non-zero, so U1 is not all of V. And U, which is the ultimate value of UI, is inside U1. Therefore, U, which is UM, this is inside U1. Okay. Not therefore, since U is inside here, U is not V. Okay. But okay, for the same reason, it also shows that K is not zero, but that is not what is required is that U is not V. Okay. And I mean, U could be zero, that cannot be ruled out. That is not that's not relevant for the proof. Okay. Similarly, K is not zero. So I should just clarify. So I can write down, let me write a few statements, which none of us will actually require in the proof. I mean, it is where I should not say. Okay, let's keep this thing. K is not zero. Okay, because K contains K1. Okay, so this is okay, so this is okay, but so far, I mean, we do not know whether K is not V or U is not zero, but this is not required in the proof. I mean, this meaning this knowledge is not required. Okay. So this is okay. So just sorry, I don't know what sort of. Maybe I should just rewrite this whole line instead of scribbling like this. But this. Okay, so I hope this clarifies this thing. Okay. Well, what I wrote in brackets will be clear when we do the proof. But I hope the thing that we know that U is not V is okay. Okay. By induction on dimension, okay, T restricted to U admits a Jordan form. In other words, there is a basis. In other words, that is, there exists a basis, okay, of U with respect to which T restricted to U is a matrix in Jordan form.
Excuse me, sir.
Yes,
Sir, can you please scroll up a bit?
yes, yes.
Okay, sir.
Okay, so this, okay, so therefore, so this is where the induction is used. That the space U is strictly smaller dimensional. It could be zero, that is okay. We will separately prove for K. That is not by induction. I mean, sorry, I shouldn't say that. There is some induction there, but that's not this induction. Okay. 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 So then, since the matrix of T for V is block diagonal uh, for the matrix of, so therefore, okay. So just as I'll write here. Uh, okay. So this is the K part. This is the U part. From these are T invariant. So off diagonal we have zeros. Okay. T does not take vectors of K into U or vectors of U into K. Okay. So this is and off diagonal is 0, and here we would get T restricted to K, and here we would get T restricted to U, okay, which we have already taken care of by induction. Okay, so we just need to worry about T restricted to K. Okay, so therefore it suffices to show that T restricted to K has the Jordan form. I mean, that is, I'm just being sloppy with my terminology. That is, K has a basis with respect to which T restricted to K is given by a matrix in Jordan form. Okay, so this is what we want, and the advantage of this reduction is that T restricted to K means that the only eigenvalue of T on K is 0. Okay. Okay. T is nilpotent on K. Okay. So note that T restricted to K is nilpotent since okay, K is Km. So Tm applied to any vector little k is 0 for all little k inside K. So it is nilpotent. Okay. Every vector is killed by some power of the of this thing. Okay. So sorry, was there a question? Okay. So the next step, now we will assume now. Okay, so we can replace V by K and assume that T is a nilpotent operator on V. Okay, replace V by K to assume that T is a nilpotent operator on V. Okay, so at each stage we are making the situation more special, but then we are also convincing ourselves that proving the theorem for that special case will prove for the general case. Okay, it just makes it easier to do this. I mean, okay, yeah. Okay, so this is okay. Any questions on this reduction? Well, so the previous reduction, I think was less less technical. This is a little bit, I mean, if you, after all this, if you go back and read the proof, this is a natural step, but maybe now it does not, it looks very, it may look strange. So if you have any questions, please ask. Okay. But so we have now reduced to the real, I mean, to the real situation, I mean, to the actual situation where we have to do a concrete calculation. Okay. Till now, it is all just some, by certain observations, we can just reduce the problem to more and more special situations. Okay. Okay, so this is where, okay, so now I want to take a break, I mean, break from the proof, I mean, not from the lecture, and let us look at one example which we looked at last time, okay, about a nilpotent operator, okay, an example. Okay, so now I'm just going to, let's look at an example before we continue with the proof. Okay, so V is this,
Sir,
yeah.
so before we move forward, can you once explain why, how by induction U has a Jordan form?
Dimension of U is less than dimension of V.
Oh,
Here, right? I mean, U is a subspace of V and U is not all of, that's because U1 is not V. I mean, U1 is the image T, but T has a non-trivial kernel, so its image is not all of V.
okay, sir.
Yeah. So, and U is inside U1. So that's also not all of V. So therefore, by induction, that has a Jordan form. Is it clear?
Yes, sir.
Okay. Yeah. Okay. Yeah.
Hello, sir.
Yes.
Sir, we are
Yes. Yes.
applying induction on the dimension of non-invertible matrices, right?
No. No. We are doing dimension on the vector space on which these things are happening. We are saying the following. Okay, maybe it's a good idea to just because, yeah. I mean, as I said, we write a lot of proofs by saying by induction this is true without ever specifying what is it that by induction that we are saying. So it's a good idea to maybe pause and look at the statement again aside. Okay, and the statement. Okay, so I will write it. If there's a mistake, we'll fix it as we go along. Okay, for all natural numbers n, unless I used n. So the notation in this aside paragraph might be inconsistent with the proof, but that's just because I just so aside. Maybe I should just write what induction. Okay, for all complex vector spaces of dimension n, and for all linear operators, complex vector spaces V of dimension n, linear operators T on V. Okay. There exists a basis B of V such that T is given by a matrix in Jordan form. Okay, Jordan form in the basis B. I mean, maybe I should probably put this here. So is this statement inside this green box, does that logically make sense? I'm not asking whether it's true or not. Okay. I mean, it is a syntactically correct statement for all natural numbers n, and for all complex vector spaces V of dimension n, and for all linear operators T on V. There exists a basis B of V such with respect to such that, sorry, what am I doing? Such that with respect to B, T is given by a matrix in Jordan form. Okay. This is a statement. Okay. I'm not asking whether it is, I mean, we're not discussing whether it's true or not. We're just saying that it is a syntactically valid statement, and we are proving this. Okay. After we prove this, we will say it is true. Does it clarify your question?
Yes, sir.
Okay, yeah. So this is what we're proving by induction, and okay. So that's why when we say by induction on dimension, this is true. We are applying this statement for smaller dimensional vector space. We are saying that this statement is true for all n less than dimension of V. Okay, so that's what we have done. Okay, yeah. I don't know. It is a good idea, at least when we all start out, to write these statements carefully a few times. After that, it will become clear that this is what is being done. But no, textbooks will not write. I mean, we also won't write. I mean, it is not the textbook's fault, or it is not. I mean, after a while, the language becomes. What is meant by that becomes clear to both the speaker and the listener. And at which point the extra things will be dropped. That's the only. I mean, it's just a natural thing. Okay. So, but at the beginning, yeah, it is better to be clear about what do you mean by saying by induction
Hello,
on
sir.
dimension. Yes.
Sir, so
Yeah.
I mean, if T is the zero map, in that
Yeah.
case, the kernel will be the whole of the vector space. So that's why we are not actually applying the induction on T restricted to K.
Correct. So that is one example where the induction cannot be applied to K. It can only be applied to U. That's one. But that's zero map is not the only issue. For example, the example that I wanted to discuss also fits into that thing. Okay, so I'll come to. Okay. V is the complex vector space of complex polynomials. Okay. Or maybe I should define the. Okay, yeah. So let us just say Ft inside Ct such that degree of Ft is less than or equal to n. Okay, so this is an n+1 dimensional. Okay. So so in this we can write T, and T is differentiation. Okay, which sends x to the T to the I, or maybe T is not a good letter for this. I'll write x. Okay, because T we have sometimes used. Okay, okay, x to the I, T of x to the I is I times x to the I minus 1. Okay, so this is for all 1 less than or equal to I less than or equal to n, and T1 is 0. So we can just, I'm just defining T. Okay, it is just that it happens to be different. This is what we would get if you these were real polynomials and you applied principles of differentiation, okay, taking limits, etc. But I'm just defining like this. Okay, so then T is nilpotent. Okay, T is not 0, but T is nilpotent. Okay, So if we do this thing for, if you do this calculation for the previous step, we would get that K is all of V and U is 0. Okay. So the only place where we can apply induction on dimension is on U, not on K. Okay. So zero map is not the only place where we cannot apply to K. It is for any nilpotent operator. You cannot do this for K because V will become all of K. Okay, other way around. K will become all of V. Okay, so therefore, one can't do induction on that side, but one can definitely do induction on the image side, U. Okay, so this is this is what we have. So now, how do we work with this? I mean, how will we prove this theorem? And looking at this will give us some intuition on how to go about proving the theorem. Okay, the final step of the theorem. Okay, but so let us do this. Okay, so here we're going to do slightly different. Okay, we're going to still prove use by induction on dimension. Okay, but the way we will use the induction and build come back to V would be slightly different. Okay, so I want to just slightly change notation. Okay, I will write N for the kernel of T. Just I don't write K itself because we just use. I mean, logically nothing. I mean, there's no problem, but just for the okay. So let and W be the image of T. Okay. Because it is T is nilpotent, again N is not 0. So W, sorry, I should probably just, sorry. Okay, let me just, okay, let us actually write down what these are. For a minute, I got carried away by the proof and not by what I want to do in the example. Okay. Okay. So what is N here? N is this. N is the complex span of the constant function. This is the set of constant polynomials. Okay. And W is, okay, so W is, so x to the n will not be there in image of T. Okay. Everything else is there. So it is the span of 1x up to x to the n minus 1. Because, okay, the T itself has some coefficient I, but that is just invert. I mean, you can just divide by that. So if I times x to the I minus 1 is there in the image, then x to the I minus 1 is also there in the image. You can just divide by I. Okay, so W is this, and this is an n minus 1 dimensional subspace. Okay. I mean, certain things are still true. They are both. So I won't write down because that observation is not hugely. I should not say. Okay. They are both T invariant.
Sir, W is n-dimensional subspace.
Sorry. Thank you. W is n dimensional. Okay. Not n minus 1. Okay. Both n and W. So Tn is 0. That's because differentiating any element inside will give 0, which is inside n. Okay. And Tw, which is differentiating elements of W, they will just decrease the degree by even further. This is also inside W. Okay. So n and W are T invariant subspaces of V. Okay. And dimension of W is strictly smaller than dimension of V. N we don't know because N could have been all of V. Okay. In which case T is 0. Okay. So in which case we know how to handle this. Okay. So dimension of W is less than dimension of V. And so therefore we can apply induction on dimension. Okay. So therefore W has a basis with respect to which T is in Jordan form. Okay. So this is all. Okay. I mean, okay. So I want to actually use a slightly different basis because I want to write down the Jordan form as such. Okay. So let me just write W as n times x to the n minus 1. Okay. So this is inside W. So I'm just, okay, maybe I should have just written that here. Yeah. Okay. So let W be this one. Okay. So then if we look at the following, W, TW, okay, so TW will be n times n minus 1 times x to the n minus 2, okay, and so on. Okay, so this is, and okay, so W is n dimensional. Okay, the vector space W is n dimensional. Okay, and so if you take this little w, okay, there is, so we can go up to t to the n minus 1 w. Okay, this is just 1. That is, if we are differentiating a polynomial of degree n minus 1 times, so we'll just get a constant. Okay, this is sorry, this is not 1. It will be some sorry, n factorial. Okay, I mean there is a reason why I would like to write it. Okay, so it is not 1 because but I would like to write it as w t w t square w and so on. Okay, and then t to the n minus 2 w is n factorial times x. Okay, so here this is n times x to the n minus 1. Okay, this is n times n minus 1 to the x n minus 2 and so on. Okay. So these are linearly independent. They're polynomials of different degrees. Okay, so their linear combination is 0 if and only if the coefficients can be 0. Okay, so this is a basis. W with respect to which T is in Jordan form. Okay, so this is just an explicit calculation. I mean, here I am just writing some inductive statement which we will use in the proof of the theorem also. Okay, but I'm illustrating it with a specific example. I'm taking a W, which is an n conveniently chosen degree n minus 1 degree polynomial, okay, and then repeatedly applying t to it. Apply t n minus 1 times. So then we'll get a non-zero constant. And these things are linearly independent. They have the right dimension as they have the right cardinal. They have the cardinality of the set is as the same as the dimension of W. So this is a basis. Okay. And with respect to this is in a Jordan. Yeah, and the Jordan form is. It's a good idea to write down. Sorry, I'm still discussing the example. Okay. So this is W, TW, etc. up to t to the n minus 1 W, and here W, TW, etc. Okay. 0, 1, 0, 0, 0, 1, and so on. and t to the n minus 1 w is 0. I mean, is a constant. So when you apply t to that, you would just get 0. So this is the n by n block of the n by n Jordan block. In fact, there's just one Jordan block. Sorry. Okay, with eigenvalue 0. Okay. So this is what it looks to in a situation where we are familiar, where we can do some calculation. Okay, so this is what, okay, so yeah.
So I still didn't understand why you took n times n x to the power n.
Oh, it didn't matter. I mean, I could have probably taken x to n minus 1. I would have gotten slightly different constants here. But I want to, the point I want to make is, yeah, I agree. The n times x to the n minus 1 is not, I mean, the n there is not, the coefficient n is not critical for this argument. All that I want is, I just want to take one w such that w, t square w, and all the way down to t to the n minus 1 w is a basis of v.
Okay, so thank you.
I just want to illustrate that point, that there is a w such that this is a basis for w. Okay. Whether we specifically multiplied x to the n minus 1, I mean, we will have to take a polynomial of degree n minus 1 for this argument to work. Okay. I just chose, yeah. Okay, but now it'll become clear why I chose that. I mean, so far we did not use it. Okay, but what is this w? This little w is t of x to the n. Okay, so I'm going to call this v. Okay, so this is now, okay, so now what is our observation? V, tv, this is just w, t square v, this is tw, and so on. T, so here we went all the way up to t to the n minus 1 v, so that w, so that would just be t to the n. Okay. Okay. Is a basis of v. Okay. Okay. So this is I mean, okay. So this w that we chose is in the image of is in the image of t. So there exists a v such that w is t of v. Okay. I just chose the specific form of w so that v looks nice. Okay. So I hope I hope that is that is just a choice. Okay, just that this v looks nice. Okay, so this is the idea that by induction there is a basis for w, okay, with respect to which things look nice. Okay, and that because w is the image of t, we now find elements in v mapping onto this basis element. So we actually don't take elements for all of this. We only looked for a v that mapped onto w. The rest we just constructed by repeatedly applying t. Okay, so this is the one that we already chose. Okay, so this is the idea that we are going to. So that's one thing. The other thing is, if we choose a different v, that would differ from this choice by an element in the kernel. Okay. So if v tilde is such that t of v tilde is also w, then t of v tilde minus v is in n. Okay, but in our case, this is something special to the specific example, okay, I mean, it may not hold in the, it will not hold in the proof in general, but it is still fine. Okay, okay. So, but in this example, v tilde minus v is n is inside W. They're just okay. So therefore, v tilde minus v is inside W, which is anyway spanned by these things. Okay. Sorry, I should not have claimed this. Is linearly independent. Okay. So we identified a W such that W, TW, etc., form a basis for V, for W. Then we took a V that maps onto this W, and then we took VW, TW, and so on. So that's linearly independent is the first observation. Then we observe that if there is some other V such that that also maps into here, then this difference will be inside inside W itself. Okay. So yeah. So
Sir?
putting all these, yeah.
So could you scroll up for a minute?
Which
A little more, sir.
this point?
No, a little more up here. Okay, yeah.
The matrix or above the matrix?
No, I just wanted to see the matrix. No,
Here, this is just a Jordan block, eigenvalue 0 and then 1 n by n Jordan block.
Yes, thank you.
Yeah. Okay. So this is how the example is. Okay. So therefore, V TV up to t to the nv is a basis. Okay, with respect to which t is basis of V. T is in Jordan form. Okay. Okay, so this is the end of the example. Okay. So we would now like to build on this example. I mean, not build, use the idea of this example to prove the theorem. Okay, for nilpotent operators. Okay, so this is, I mean, the most accessible example of a nilpotent operator is the differentiation. So yeah. So okay, and the key thing that we are using is that it is sort of shifting the basis elements. Okay? The first basis element gets moved to the second goes to the third goes to etc. The last but one goes to the last, and the last goes to 0. Okay, this is how. Okay, I mean this is how one Jordan block of a nilpotent operator will look. Okay, so that's okay. So of course in the general case it may not be one Jordan block. So we'll have to handle all those things. But the key idea comes to this. One, find that maps onto the function in that case. And then we just repeatedly apply T to get for the whole thing. And then this is okay. So now let's continue with the proof. Okay, so the statement is, recall, okay, T nilpotent operator on V. Okay, that's where we are. T is okay. Okay, so that's yeah. So we just need to prove the theorem for nilpotent operators. So again, so let N be the kernel of T, W be the image of T. Okay. So N is not zero. Okay. So W is not V. So by induction on dimension. Okay. So I want to write this. Okay, maybe I'll write the induction on dimension. Okay. There exists a basis. With respect to which I should not accept my notation now. Okay, so there exists a basis of W with respect to which T restricted to W is given by a matrix Jordan form. Okay, so this is what we know by induction. Okay. But I want to rewrite this because working with actual basis elements, etc., will introduce somewhat tedious notational issues. So I want to rewrite it in a sort of coordinate-free, basis-free fashion for a okay, but equivalently. So okay. So I'm just rewriting this assertion for W in an equivalent fashion. Okay. There exist subspaces there exist T invariant subspaces W1 through WR of W such that W is the direct sum and T restricted to WI, it's T invariant. So we can okay, when you restrict T to WI, we will just land inside WI. Okay. Okay. This of course is a nilpotent operator because any element, for an element inside WI, this is just applying T. So if you apply T enough times, it'll become zero. Okay, so this will, okay, so T restricted to WI, okay, is given by a matrix that is one Jordan block. Okay, so I'm making a slightly stronger statement. Here I am just saying Jordan form, which means it is block diagonal and each block is a Jordan block. Okay, so now I'm saying, so I'm just rewriting this. So all I'm saying, doing is just elaborating the statement. It is nothing. I mean, that's why it's equivalent. I'm not introducing any new. I mean, I am not proving anything new. Okay, I mean, these are just restating. So there exists a basis with respect to which the matrix is in Jordan form. So then it is in a block diagonal fashion, with each block being a Jordan block. So you just collect the basis elements corresponding to each Jordan block and define these subspaces WI. Or conversely, if you have this description, then just get a basis for each of the WI, put them together, as a basis for W, we will get the matrix will be in Jordan form. Okay. Okay. So this is so on each Wi, it is just one block. Okay, that's the only thing. So this is just elaborating what this means. Okay. So I mean, just it is only just rewriting. It may not. I mean, the sentences are so long that it may not be immediately. I mean, perhaps it is not obvious that these are the same description, but please read it after the class and you'll realize that I'm just restating what we know. Okay, but it is important. It is easier to do it this way. Okay, otherwise the notation will become cumbersome already. Okay, so for each 1 less than I less than R, let little wi in capital Wi be such that wi, twi, all of these are inside capital Wi, up to t to the ei minus 1 wi is a basis of wi. Okay, so this uses the fact that t restricted to wi is one Jordan block. Okay. So if an operator, okay, so this is, so let me just, so this is where the one Jordan block is used. That there is a one vector such that wi, t square wi, and that thing. Okay, so here ei is the exponent of, I mean, as a generalized eigenvector, exponent of wi. Okay. We have used. Okay, maybe I should just. Okay, here. Okay. Okay. We observed last time that if you have one Jordan block, there is a vector that would generate the, I mean, whose image, successive images under T will give a basis. Okay, so so that we have used here. Okay. One Jordan block is okay. So this is a basis for wi. Okay. Okay. So now, okay. So now a basis for W is yeah. So note also that EI is also the dimension of WI. I mean, all of it is sort of hinging on this fact that T of WI is T restricted to WI is one Jordan block. Okay. That's the reason why I needed to. Okay, that's not exactly the reason why I needed to rewrite. It is to reduce the number of vectors that you have to keep track of. So we will not. It is not necessary to keep track of this TWI, T square WI, etc. Just you need to know WI. Okay. For each I, we just need to know WI. From that collection, we can generate the whole basis. Okay. So therefore, so note. Okay. If you take T, this collection, T to the J, WI, 1 less than or equal to I less than or equal to R, 0 less than or equal to J less than or equal to EI minus 1, okay, is a basis of W. Okay. So instead of writing these as things, we just keep track of these WIs. Okay. So now, so what did we do? in the example. Sorry, maybe I should just pause for some time, let you read this. Then I just want to go back to the example. Okay, maybe I'll say what I want to do in the example. So in the example, it was convenient because there's only one, W was only one Jordan block. Okay, the example was that differential example of differentiation, and W was all polynomials of degree less than or equal to n minus 1. And that was just one Jordan block. Okay. And that okay, so that's its first basis element. We lifted to, we took something in V that mapped onto the first basis element, and then we created one for the entire vector space V. Okay, so we're going to do the same thing here, but here we have R Jordan blocks for W itself. Okay, so we need to take care of that issue. Okay, so let me just whatever I said in the example, let me just go back. Yeah, W itself was one Jordan block like this. So we looked at the first vector in that nice sequence of basis elements that we constructed. Okay, took a V that mapped onto that W, and then we took V, TV, which is W, T square V, which is TW, and so on. Okay, and then we proved that this will work. Okay, so we're going to repeat this thing, except that we have to do this for each of these blocks here. Okay. So for 1 less than I less than or equal to R, let Vi in V be such that Wi is T of Vi. Okay. So for each one of those Jordan blocks of W and the little Wi, which generates using T a basis for Wi, okay, we take one Vi. Okay, so this is what we have done. Okay, so now let me write down. Let me make a claim. Okay, so let B be this large collection of vectors, which is what is it that we are going to do. Okay, so we start with the Vi, and then we apply TVI. This is just Wi. Then we apply T square Vi. This is TWI, and so on. T to the times Vi, which is the EWI. Okay, so we for each one of these i's, we look at this sequence: Vi, TVI, T square Vi, and so on. Okay, and take this collect union. Okay. Okay. So we will claim that this collection is linearly independent, okay, and we will prove it. Okay. And then we will show that after we may have to still add some elements from the span of n, the kernel of T, to this, and then we will have a basis for V. Okay, so claim B is linearly independent. So remember, I mean, our okay, so we want to build a basis for V. Okay. So this is the candidate. This is not all of it. We still have to work on it. Okay, but we have a good candidate. And if you take any with respect to this basis, okay, if you apply T to any one of these things, we will just go to the next vector. Okay, so this is the Jordan form. This has the desired Jordan behavior. Okay, that's the reason why And this is also disjoint union. Okay, okay, so linearly independent. That will okay. That is a disjoint union will become clear from the proof. Okay, so proof of claim. I mean, this set cannot have intersection. I mean, pairwise non-trivial intersection is will follow from linear independence. Okay, so proof of claim. Okay, so suppose that some alpha ij, okay, I goes from 1 through R and j goes from 0 through ei, t to the j, vi is 0. Okay, so we can apply t to this. Alpha ij, okay, tj of tvi is 0. Okay, but this is just wi. Okay, of course, j equals ei. This is already 0, so that is not that doesn't contribute. Okay, but it says that. Okay, so this is 0 inside w. This is a linear relation among a basis for w. Okay, so this means, I mean, except if you drop. Okay, so one of the indices won't appear because that. Okay, so this note TEI of WI is 0. Okay, so they should not be counted. Okay, so this says that alpha ij is 0 for all I. Okay, and for all 0 less than or equal to j less than ei, because the the value, I mean, t to the ei don't, I mean, they anyway don't contribute. So it's the other thing that is 0 that you can conclude. Okay. Okay. So this is what less than ei. Okay. So then we just have to worry about. So this implies that sum over alpha I ei, I mean alpha I ei, t to the ei vi is 0. Okay. But this is already inside w. So this is just, okay, this is just t to the ei minus 1 wi, right? And this is a linear combination of linearly independent elements inside w. So this implies that alpha I ei is 0 for all 1 less than or equal to I less than or equal to R. Okay, so together, okay, so this proves the claim. Okay, so this is the, I mean, this is the main step going from W to V. Okay, so we have now identified, I mean, a good collection of linearly independent vectors inside inside V, such that if you apply t to one of them, we just go to the next vector. T applied to Vi, we just go to TVI. It will not go to some Vi prime. Okay. So this is okay. So this proves a claim. Okay. Any questions about this thing? Yeah, I agree. You may have to read it again to make sense. Yeah, if you have questions, you can ask or email or I mean,
So
if
can
you
you scroll up again?
up, yeah,
No,
to the beginning
no, just below. Or
here.
just the last line, just last few lines. Oh yeah.
Okay.
Oh, okay, sir. Got it.
Okay. So this is okay. So this is okay. So now, yeah. Okay. So now let's define. Okay. So let Vi be the complex span of little vi and so on. Okay. That is in this union of linearly independent things, the span of the ith piece in the union, call that thing Vi. Okay. And U to be, the proof now says that since B is linearly independent, okay, the sum V1 up to VR is a direct sum. Let U be their direct sum. Okay, so B is a basis for U, and it is, I mean, their pairwise intersection is trivial. So any element in the sum can be written uniquely as coming from V1 plus something coming from V2 and so on. Okay. Okay. So again, U need not be all of V. We still have to work on that a little bit, but the observations that we would want to make now is that with respect to B, T restricted to, so first observation is that TU is same as W, because if you take any vector inside, maybe it's easier to write other way around, since Wi is equal to TVI. Okay. I mean, if you take Vi, which is a span of this, and you apply T to it, you would just get W. Right. Okay. We see that TU is TU is, we see that W is inside TU. Okay, which of course is inside W because this is TV. W is the image of T. Okay. Okay. So therefore, TU is W. Okay. So everything that is there in W has been obtained from this subspace of V. Okay. So the only thing that we need to take care of now are elements in the kernel that don't, elements in V that didn't go to elements in W. Okay. That's, that didn't go to non-zero elements in W. That is, okay. So, okay. So this is what we need to take care of. So TU is W. Okay. So now we want to make another claim 2. Maybe why are we making it? So let's make an observation. If you restrict T to U, okay, is in Jordan form, okay, with respect to B. Okay, B is a basis. Maybe one should clarify that also. B is a basis of U. It is sort of clear from these two statements. I just want to emphasize it. Okay. That is because the same same thing that we just said. If you look at this collection and apply T, we just go from one vector to the next one. Within each sub collection, we will not go from any collection, any sub collection to it. We will not go from one sub collection to some other sub collection. Okay. T sort of stays within these sub collections. Okay. And inside that, we just go from some one vector to the next one. Okay, so this is that's this P restricted to U is in Jordan form with respect to B. Okay, sorry, I just need to finish this proof. So I will go a little bit, but please bear with me. Okay, so this is with respect to B. So now we just need to finish this form. Okay. So claim 2. V is U plus N. Not necessarily a direct sum, because remember W is inside U. Okay. So, but N is part of N. I mean, there are parts of W that's also in the kernel because of nilpotency. Okay. So it is not. This is not a direct sum. It is just a sum. Okay. Proof of claim 2. Okay. Let V be inside V. Okay. Then there exists U inside U such that TV. So TV is inside W, but W is also TU. Okay, that is, but this implies that V is inside U plus N. I mean, this just means that V minus U is in. God, what am I writing? V minus U is inside N, right? This implies that little v is inside U plus N. So, I mean, proving this claim. Okay. So we have already identified a basis B of U with respect to this. This is Jordan form. Okay. So now, therefore, we can extend B. Therefore, we can enlarge B to get a basis B prime of V with, I mean, we can enlarge B with elements of N, okay, to get, maybe I should not write it in English to get an ambiguity, okay. Therefore, there exist elements Z1 through some Z M inside N such that B union, this of course is a disjoint, maybe I should not say, B union Z1 through Zm, this M is a basis of V. Okay. I mean, again, I mean, the general case, I mean, proof axiom of choice, B is not the whole space. You can pick one element, keep doing it, not, and therefore it will stop. You don't need axiom of choice. I mean, or depends on how we have proved existence of basis. But anyway, you can pick one. I mean, if U is not all of V, then we can pick one element in N, which is not inside U. Okay, so you keep add that, and then you repeatedly do this. At some point, it has to stop because dimension of V is finite. Okay. Yeah, basis of V. So let me call this thing B prime. Okay. So
for finite dimensional cases, the choice function is like explicitly can be written. So what's the
yes, I said axiom choice with the general situation, but yes, here it's not required.
but in the general situation, you said that the finite dimensional basis. So
No. I was just
So it must
sorry.
end.
I was just yes. The thing is, here we know that it must end, right? Yeah.
Okay.
Yes, I take my comment about axiom choice. I mean, I take it back because yes, it is not at all required in this case. Yeah, with respect to B prime, T looks like T is given by okay. So I just call all of B here. Oops, sorry, I am really over time. But if I okay, this things I will call Z1 through Zm. Z1 through Zm. And this is B. So this is T restricted to U, which is already in Jordan form. Okay, and Z's are all in the curve. I mean, okay, and this is anyway block diagonal because it's this is T invariant subspaces. Okay, so we have 0 here, and 0 here because since Zi is inside N for all. Okay, so this is the proof. So I'll stop here, and we'll do some comments in the next lecture about this. And I'll okay. Sorry, I stop now because it's way over time.